Christopher Davis is a PhD candidate in archaeology at the University of Illinois in Chicago. Chris's research interests are in Amazonian and Circum-Caribbean archaeology, rock art and cosmology, archaeoastronomy and landscape recognition, and paleoenvironment. In 2009, Davis was awarded a Fulbright Scholarship for his Brazilian dissertation research and participated as a Fine Outreach for Science Fellow. Please join me in welcoming Chris here.
All right, thank you. For today, I'm actually not going to present information about the archaeology that I do. I was kind of asked to present something like a workshop where people can kind of interact with the material. So if you do have Gigapans or your computer, you might be able to kind of work alongside me. A lot of the stuff that I am about to present today, I kind of came across sort of by accident. I'm kind of notoriously thinking about things after the fact that I really needed them, and this was one of those examples. So when I was actually doing my dissertation research out in the field, I had a Gigapan unit, and I kind of was just taking pictures of things. I actually had the unit before I actually learned how to use the unit. So I kind of figured that it would be a good idea to take a lot of pictures, but I didn't know exactly how I could use them at the time. Once I came back from the field and I stitched together a lot of images, it started to occur to me how I could actually use this information. And so one of the ways that I needed to use the information relatively recently with my research was that I needed to kind of determine height in some of the pictures. I study rock art, and actually I ended up having to study a little bit about archaeoastronomy as well. So it really became important to me where things were positioned relative to one another. So actually this workshop is designed with the concept that many of you might have Gigapans already, and you might be thinking about ways where you can interact with them. This is really a very informal workshop in the sense that most of you, if you're doing hard science, there's a lot of other more accurate ways that you can determine dimensions in photographs or beyond photographs using laser transit and the like. So this really is kind of in its infancy, and I figured that I could present the information here and see where other people might be able to take it. So with that in mind, the objectives of this workshop is to determine measurements and dimensions in panoramas, but that is a little bit of a misnomer, because really what we're doing is we're determining dimensions in a particular image plane. So there's all sorts of difficulties when doing that, because an image is dynamic. It has different distances, it has different angles, but nonetheless there are some things that I've been looking at that it looks like we can be able to determine some of the differences. So again, this is a very general, very loose kind of estimate of targeting height or width of objects in an image. And then once you do that, actually, if you can determine an image plane, you can actually perhaps overlay that with a grid in any sort of imaging software or mapping software, and then that could give you general distances. It's not an exact solution, but it is a beginning. And here, I really just did this Gigapan. It's not a good Gigapan. I did this Gigapan for this workshop just to kind of give examples. And so you can see here I have this image, and it's distorted. But the image plane, which is actually the front of the stadium, is the distance has been determined and the like. So this grid that you see, it's in meters, and it actually gives a rough estimate of the distance of the stadium, at least on the outside, that's facing closest to me. So between 20 meters and a little under 200 meters, so about 180 meters long. This is Soldier Field. This is in Chicago. Okay, so the first thing, what you would need if you were to try to determine dimensions in your Gigapan panoramas, it certainly would be helpful if you had a distance to your actual image plane. So if you're determining something like a solid wall in front of you, it would be helpful to have a tape measure going directly out. That's a single plane. It's very simple to kind of determine that. But I'm sure many of you are thinking, how often are you in the field with a tape measure, measuring from your camera to whatever you're filming? In many cases, you guys are going to be taking images of things that have all sorts of different distances. The other thing to note is that the Gigapan stitcher, once you do stitch your images, actually maintains some information that's going to be very helpful. The focal length, which is helpful, but you actually don't really need to know the details of the focal length for kind of these simple calculations. But sometime later that might actually come into play. Also, the field of view, which is very, very useful. The field of view tells kind of the angle of the height and the width of the entire image. And that's kind of the crucial key to determining distances in a Gigapan. Also, one other note is to kind of pay attention to the curvature of the image, or the overlap of the image. The more percent overlap that you have, as you might be able to see down here, horizontal overlap 40%, vertical overlap 58%. The more overlap you have, that kind of indicates how much curvature the Gigapan is going to have. So again, that's going to be helpful down the line. For now, just kind of keep that in mind. Okay, now I actually don't really know how the Gigapan people stitch together images. So I'm sure some of you actually probably know this a lot better than I do. But the simple stuff that I do know that I can try to explain really quickly is that when you take a single photo with a camera, it's converting a three-dimensional world into a two-dimensional image, so it sort of flattens out things. The Gigapan stitcher then takes a bunch of those two-dimensional images, stitches them together, and in many cases it's actually kind of projecting that flat image into a spherical projection. And this becomes obvious when you do stitch the image and you can zoom in and out. You can see kind of the curvature of the image. This is before you export it as a TIFF or a RAW file. You could sort of see the curvature of it. So it's really kind of a projection of a flat image that was taken from a three-dimensional world. So there's all sorts of levels of, I guess, corruption in the image or distortion in the image, which currently you can't really account for. The stitcher is constantly being improved, and the most recent stitcher has less distortion. And in the future, they'll probably have even less than that. But for the time being, I'm noting that because it is a source of error. So these sources of error will build up as I go along. Okay. Also, it is helpful when you are taking your Gigapan out into the field and you do the initial setup, where it says set the horizontal, set the camera to the horizontal plane. It is helpful if you can, to do certain calculations, to set it parallel or horizontal to the camera. That can come in handy later because it's helpful to know kind of right angles to a particular image plane. But that isn't necessary. It isn't necessary all the time, but certainly if you can do that, it's helpful. All right, and finally, it is also helpful to have some sort of imaging software. This here, I use Map Viewer. You can use Photoshop, of course, any other sort of imaging processing software where you can measure distances. That's the key thing. You want to be able to measure distances on the map, whether it's distances in pixels or kind of generic relative distances. But it's really important that you have a way to kind of measure the distances. Okay, now, After the image is stitched and loaded in an image processor of some sort, you will be able to measure the overall length of the image and compare that to the length of a particular target. So in this example here, I have the Sears Tower. Hopefully you can see that. It's over here. The Sears Tower is what I actually want to measure in this image because this wasn't the original target. The original target was Soldier Field, and it was just kind of a quick Gigapan. But the Sears Tower, I can find the height of that online. So I looked for Soldier Field, and I couldn't find the height of it. So I wanted to have something that I could find the height of to check the values that I calculate. So in this case, I'm using the Sears Tower in the background. It is actually toward the end of the image where there's quite a bit of distortion, or at least the image is where the image started curving. And so when I measure the overall image, I want to measure the overall image at that point, not in the center of the photo. And as you can see here, I started this kind of cursor where the actual image ends, not where the, well, actually the actual image has further black areas. This is not part of the original Gigapan image. This was when I exported it to TIFF. So the overall image goes from this point to this point. And you could also, here I'm measuring vertical distances, but you could also do this horizontally. In some cases, horizontally would be easier, especially when you're taking a 360-degree panorama, because you have an entire full projection of a spherical surface. Okay, so here's where things get a little bit, if you're not used to geometry, it gets a little bit hazy here. The field of view, which was from the Gigapan Stitcher information, it covers the angle of the entire image. So where I measured from, that's where it's covering here. Now the target is the Sears Tower. I want to determine the height of the Sears Tower in the image. Now actually this image is not the best image also for one major crucial reason, which is that technically I can't see the base of the Sears Tower. When I took this image, it was actually dusk, so by the time the Gigapan panned over to the end, it became really dark. So I can't really see the base of the Sears Tower, but I kind of estimated that this was the base here. But nonetheless, the target angle is going to be a percentage of the field of view angle. Now this much is going to be retained with the image. So this much, there's less corruption. The only real major source of error here is where I'm placing the cursor to measure the distances. If I'm off, it can cause problems in calculations down the way. Now, the other part of the equation that is going to be crucial is the distance. Once again, I said that it would be a good idea to measure the distance to the target, but oftentimes you don't have a tape measure or the distance is way too far or something of that nature. There is one possible solution if you're outdoors, and that is that Google Earth actually has a measurement tool. So this kind of aspect is really nice because it's combining two different technologies that are already kind of working together anyway. So here I have a Google Earth image of Chicago. This place here, although it's not labeled, is the Sears Tower. And using Google Earth, you can use the ruler tool and draw all the way over to where I had my Gigapan set up, and it gives me the length, or rather the distance. And they have like a little pull-down screen. You could change between meters, feet, kilometers, miles. So the distance can be determined through Google Earth, at least when you're outdoors. Okay, so when I said that the image is kind of the Gigapan image is a projection on a spherical surface, that's kind of where the calculations come in handy. Because if you're on a spherical surface, at least to a particular image plane, you essentially have a circle. Now, technically you have a sector of a circle. Now, the sector of the circle, you can determine the angle of that sector by determining, if you have the distance, you could determine the circumference, and you can take kind of the percent of 360 that the sector makes. So, so we can, here we've got L labeled as kind of the length in this example. R, the radius, would represent your distance, and the angle theta here would represent your field of view. Another possible solution, depending on how flat or how spherical your projection is to use trigonometry. And I don't know how many of you remember trigonometry from high school, but actually I never learned this in high school. I only learned this when I started tutoring high school kids, was that they have this nice kind of, I guess anagram, I don't know what you call these, anagram or something, SOHCAHTOA, right? So sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, tangent equals opposite over adjacent. And tangent, the tangent of an angle, such as a field of view, is going to be equal to the opposite side. In this case, it could be the height or the width, if your camera angle is 90 degrees to your image plane. So again, that's why earlier I said it would be helpful if you set up your horizon to horizontal to your camera. And the adjacent side would be equal to your distance, so the distance from the camera to your target. However, most of the time, it's more helpful to use the circumference equation, and I'll try to explain a little bit of that later. Okay, so here we have an example of, once again, Soldier Field. And you can see this is what it looks like right after I stitched it. And you can see it's very curved. So in this case, because it's very curved, it's probably a better approximation to use the circumference. Typically, with a lot of these Gigapans, it's probably a better approximation to the real distance to use the circumference of a circle. So when the Gigapan has many rows or many columns, and there's a good deal of percent overlap, the image is curved, and it would be a good approximation to use the circumference. However, there are times where the kind of the curvature would not be ideal, such as when you're gigapanning something really close up. I haven't tested out any of this for, I guess, micro gigapans, so I don't know, if these formulas would work if you're gigapanning something that close up. The tangent formula, once again, that is only really useful when you're sure that your camera is at a 90-degree angle to your plane, your image plane, and that your image plane is relatively a flat vertical surface. And even in that case, you're going to have some corruption in the image because the image itself is kind of projected spherically. Even if it's a little spherical projection, it's still going to be off from a true right triangle. Okay, so if you have an accurate distance to the target plane and you have a field of view, the angle of the field of view, you can calculate the overall distance of the image at that target plane. So again, I have here, I'm showing that soldier field image, and I've overlain this kind of rudimentary graph. Again, the image plane in this case is right in front of Soldier Field, so the further, if you go out to the sides, it's not accurate. If you go, off to the distance, the actual grid is not accurate. But again, the original issue here that I wanted to test out was if I can measure the distance of the Sears Tower. So this overall grid won't be helpful for that, but the relational angles will. So the target angle compared to the image angle is still a distinct ratio. And the distance that I could determine through Google Earth is still a true distance. So with that in mind, we're back to this formula. So if I've got here the image height, which I had measured from the literal image, the target height also, Once again, you can do this in Photoshop or any sort of software that kind of has some sort of measuring tool, measuring pixels, measuring some sort of numbers. In this case, it doesn't matter because we're just looking at the ratio. So it doesn't matter if it's pixels or if it's centimeters of the image. We have a ratio, which is the target angle, which is this angle here, over the field of view angle, which is here, which also is in the Stitcher notes, is going to be equal to the target height, which is the height of the Sears Tower here, over the image height, which is the full image here. So if I'm looking, for example, if I'm trying to find the target angle, that's my unknown. All the other variables I can determine, and I can find the target angle that way. So the target's true height is going to be then equal to the circumference of the circle divided by the sector of the circle times the 2 pi distance. Okay, so let me reiterate that. Okay, so again, the idea is that the Gigapan has part of a circle here. That this true target height is the Sears Tower. It's been kind of reprojected in a spherical plane through the Gigapan, and that we are determining the overall circumference and dividing that by the sector circumference. And the ratio between the two is equal to 360 degrees, which is a full circle, or rather, the target angle divided by 360 degrees. So the target angle is a sector angle, and 360 degrees represents the full circle. So here we just have 2 pi times the distance, which would be the radius of this kind of imagined circle. And then we're taking the percentage of that circumference to find what the actual distance of that sector is. So hopefully that was clear enough. Okay. Alternatively, when you use the tangent angle formula using trigonometry, you don't really need to do the circumference. You're taking just the angle of the target here, and you're doing the target. The tangent of the target angle is going to be equal to the opposite, which would be the target true height over the adjacent, which is the distance. But again, for this, you really need to ensure that you have a 90-degree angle to that target. So when you actually had your camera set up, was it set up 90 degrees to the true target? And that's very hard to determine. So, okay, now conversely, if you know the real height of a target, you can work backwards and determine the distance that you were from that target. So if you're not outside, let's say you were gigapanning something inside, and you don't know the distance that your camera was to the target, but you do know how tall the target was supposed to be, you can work backwards to figure out the distance. So the beauty with the math is that it works both ways. It's an equation, so if you have one variable that's missing and the others that you can account for, you can calculate it backwards. All right, now obviously this is I was just experimenting with a lot of this stuff, and lots of things can go wrong. So when things go wrong, there's several ways things can go wrong. You forgot to measure distance, for example. That would be probably the worst thing that can happen. But again, as I mentioned earlier, if you were gigapanning outside, it's a possibility that you can find that distance with Google Earth. Just make sure when you turn on Google Earth that you orient the camera directly downward so that you have just kind of the distance instead of an angled distance. So once you angle the camera downward, you can use the ruler tool and measure the distance to your target. Okay, other possibilities for when things go wrong is when you're dealing with a surface that's entirely contorted. There's no kind of image plane that's consistent. This Google Pan image is actually, it's actually the site where I work at, It's kind of up high on the wall, and the actual wall itself is curving away from the camera in both vertical and horizontal. So this image is entirely useless in terms of determining dimensions. I would not be able to determine dimensions with an image like this. Also, if you're dealing with images that are at an angle to the camera, this was a Gigapan I took of the beach in Chicago, I think last summer, and the angle just kind of goes away from the camera. The image plane in this case is never consistent also. It's constantly going further out. So at least with the kind of the calculations that I've shown you so far, I would have a hard time calculating information in this image. I think that there are ways to get around this, but it would take a lot more time, a lot more calculations, which I haven't worked out yet. Okay. Also, if the target that you're taking a picture of, if that is also distorted or angled in some way, actually just by the software itself or by your photos, there might be quite a bit of distortion in the image. And so, again, the best you can do is estimate. This is actually a memorial. This is actually right behind where I took the Soldier Field image. And the memorial seemed like it was relatively flat, but it really wasn't. It was curving away from the camera once again. And so the angles between its natural curving away from the camera and the Gigapan stitching, curving it, trying to curve it toward, just kind of makes things too hard to keep track of. Now, there are some things you could try to correct for. You could try, in theory at least, to take an image and correct it yourself. There is a part in Photoshop where you can export an image into Photoshop. You can use the distort image tool, and there's a lens correction under the distort image. You could try to kind of erect a fake plane, a vertical plane from an image, but I haven't done that. Actually, I've tried to do that, and I found out that when you start to distort the image, that actually throws off the field of view versus the target angle, and so without those ratios staying the same, these calculations fall apart. Okay, now that was all of the kind of the background behind that. So getting to kind of the actual fun stuff, was I actually able to calculate the Sears Tower from using these methods? Here I've got two pictures. The first one shows the overall image height. The second one shows the target height of the Sears Tower. I've got here the stitch notes, which have the field of view right here for vertical, which is 24.4 degrees. I decided that I would go with using the circumference formula because there is a good deal of curvature here. So I figured out the target angle through the ratio of the two distances. And the target angle is 9.8997. So ideally, this angle from the camera to the Sears Tower was 9.8997. Okay, and once again, the distance that I calculated using Google Earth, if you can read that, it's actually 2,561.09 meters. So using the formula, target true height equals 2 pi times the distance times the target angle divided by 360 degrees. The calculated height that I have here is 442.5 meters. The Sears Tower true height, at least according to Wikipedia and other sources, which are always very reliable, is 442 meters, not including the antennas. Okay, now, so I sort of manipulated the software, right? Because the first time I tried it, I got numbers that were off. But nonetheless, the information is there, and yes, this was an actual true calculation, and you can actually calculate. But I figured, you know, how well could this work in other things? So I went back to one of my first Gigapans. It was of the Phipps Botanical Garden when I was here last year. And I used the same technology to try to calculate the distance of the Phipps, I forget what this is called, but the actual glass structure. In this case, I used just Photoshop to measure the pixels. So I've got here, this white line shows the image pixel distance, which is listed up here at length. It was 4,919 pixels. The target length, which I had measured just from the ground to the top here, was 1,889 pixels. The distance, I went to, once again, Google Earth, and I am pretty sure that that's where I was standing about 18 months ago when I took this photo. So I measured it out, 857.7 feet. I decided to keep it in feet. I could have used meters or something else, but feet was fine. And the field of view from the Stitcher notes, which was listed down here, Stitcher notes, 8.6 degrees high. And this I just pulled off the website because I don't even have the data for this image anymore on my computer. So using the calculations, I figured out that, once again, I used the circumference formula, height equals 2 pi times the distance of 857.7 feet times the angle, which was 3.304 over 360 degrees. I came out to a height of 49.54 feet. Now, this one I actually don't know what the height is. I think they said somewhere it was 65 feet, but I'm pretty sure they're measuring from the kind of ground level up, which is below the level where I took. But I figured maybe one of you, since you guys probably photographed the Phipps Botanical Garden too, maybe one of you have that information. You can tell me if it's close to maybe 50 feet. Hopefully it is. Okay, that's all I have. Hopefully, again, this stuff is just kind of rudimentary so far, but I was hoping that maybe some of you could build upon this. There's a lot of sources of error, but you know, working with the information and testing on certain different surfaces, different angles, eventually I think that people can build on this, and we will be able to have some sort of a measuring tool with Gigapans. And you could go back and maybe use Gigapans that you've taken a year or 2 years ago and pull off actual data from those Gigapans. Once again, that data is not as specific as like a laser transit or something, so if you're doing like highly scientific information, you probably wouldn't want to rely on this. But if you are looking at just kind of fun with your Gigapans, this might be a good way to go. Yeah, I don't know if you want any questions.
So we have about 5 minutes for questions.
We're going to start right at 2:15 to this special guest. So we have 3 minutes for questions.
Okay.
Thank you.
Are there any questions? Yes.
So, have you kind of experimented with like using, I mean, I do it with ArcGIS, but actually manipulating the image to have a known
To have a known, you mean to drape it on an actual vertical surface? Actually, I haven't experimented with ArcGIS yet. I do have ArcGIS, but I haven't.
I mean, anything that you can geo-reference in.
Yeah, I've experimented with that a little bit with Photoshop, and Photoshop's lens correction is not nearly as good as ArcView's kind of draping feature. But again, what I did find was that the problem, like you would want to do that before, or rather after you take the angles, because the ratio of the field of view compared to any target in that Gigapan is going to change once you start distorting the image. And once that ratio changes, you can't really rely on the calculations.
We probably have time for one more question.